Ever try to like explain something super specific? You know, where you have all these conditions and it's like your words just aren't precise enough.
Yeah,
Well,
totally.
maybe you've messed around with some software and you give it what seems like clear instructions, but it's like it just misses the nuance.
Right.
It feels like for all its power, everyday language sometimes just isn't cut out for like really complex rules or for building systems that truly understand what we mean.
That's a perfect intro, actually. That fuzziness you're talking about, that's exactly where we're starting today. We're diving into first-order logic, FOL for short.
Okay.
Think of it as a system built for crystal clear thinking,
Mhm.
representing knowledge without all the vagueness we get in normal conversation.
Okay, first order logic. Sounds kind of formal.
It is.
We've talked about propositional logic before, right? How does FOL relate to that?
Right. Propositional logic is like dealing with whole statements as just on or off, true or false.
Right, right.
It's fine for some stuff,
Yeah.
but it treats every fact as this single, unbreakable unit. FOL takes it way further, though. It lets us talk about specific objects in the world and the relationships between them.
Hmm.
So instead of just those on-off switches, we have this system where you can describe each piece and how they connect. FOL can express so much more.
So, listener, why should you care about this FOL stuff? Why spend time on it?
Because understanding FOL is like peeking behind the curtain of how AI thinks.
Okay.
A lot of AI and computer systems in general use logic that's rooted in FOL.
Hmm.
So it gives you this much deeper understanding of the tech around us. Plus, it can even change how you think about organizing complex info, making it super clear. That's what we're going for today.
Aha, moments galore.
Exactly.
Today's deep dive is based on a chapter that goes really deep into these representation languages, exploring FOL, comparing it to how we use language, even how our brains might represent knowledge. Big stuff.
Huge. And to kick things off, let's zoom out for a sec. Think about representation languages in general. We use them constantly. Programming languages like Python, Java. We use data structures to hold info, a list to show things in order, for instance. Databases, like SQL, also keep data organized.
Right, like a table listing, say, products and prices.
Yep. But what these procedural languages and databases often lack is a way to automatically figure out new facts from existing ones based on logic.
Okay.
In code, you got to write specific instructions to handle every condition. Propositional logic, though, it's more declarative.
So more about stating what's true, not how to figure it out.
Right. And another thing that data structures and databases struggle with is expressing uncertainty directly.
Hmm.
It's hard to say the issue's in module X or our module Y, or if this service fails, then that part is affected.
Right, they usually hold just one value, maybe with a unknown placeholder.
Yeah, no built-in way for those or if-then relationships.
Gotcha. So propositional logic handles that declarative style, partial info, or as is nots
Oh.
better.
And it's compositional too, meaning the meaning of a complex sentence is built from the meaning of its parts, predictably. If rain means raining, windy means windy, then rain and windy means both. Right? You wouldn't expect it to suddenly mean something totally different.
Makes sense. But the source mentioned that even propositional logic hits a wall with lots of individual things.
Oh, yeah?
It brought up the Wumpus world again.
The wumpus.
Remember, we had to make a separate rule for every single square, linking breeze to pits.
Yep.
Breeze in 1101, if and only if pit in 12.0 R pit in 2.4, and so on for every square. Gets really messy really fast.
Totally. In English, we just say squares next to pits are breezy. English, like FOL, has structure for these more general descriptions. That's FOL's strength, concise, general rules, something propositional logic couldn't quite do.
Which brings us to language itself as a way to represent knowledge. It's so natural to us, right?
For sure. For a long time, people thought natural language was the ultimate knowledge representation system. Just decode its rules and boom, AI can use it directly, tapping into all the knowledge ever expressed.
Ambitious. But that view has changed, hasn't it?
Big time. Now it's more about communication. Like think about saying over there while pointing.
Yeah.
Those words alone don't tell you where. It's the context, your gesture, the environment.
Right.
So natural language relies heavily on context, making it tough to use directly for AI. How do you even represent that context accurately?
Good point. And then there's the classic ambiguity problem. One word, multiple meanings. The source quoted Pinker using spring, the season, or something that bounces.
Right. If one word means different things, then thoughts can't simply be words, at least not for an AI that needs things super precise.
True. Which brings us to the Sapir-Whorf hypothesis, the idea that the language we speak actually shapes how we think about the world.
Intriguing, isn't it? Worf thought different languages categorize reality in fundamentally different ways, and this shapes our thought processes. Now, his original strong claims have been debated, refined by later research, but there's definitely some evidence that language can subtly influence thinking.
Like those Gugu Yimithir speakers, right? The ones in Australia who use absolute directions.
Exactly. They don't have left, right, just north, south, and so on. And studies suggest they have this amazing sense of direction, much better than us relative direction folks.
That's wild. So language shaping a specific cognitive skill?
It is.
And the source mentioned how grammatical gender can affect descriptions.
Oh yeah, the bridge example. Masculine in Spanish, feminine in German. When asked to describe a picture of a bridge, Spanish speakers use words like strong, sturdy, while Germans go for beautiful, elegant. Crazy, right?
It is, like the word itself guides our thoughts, similar to that car crash experiment, right? Loftus and Palmer, I think.
Yep. Just changing the verb from contacted to smashed made people remember the cars going faster. Language affecting memory. But the general consensus is these are subtle influences, not like huge worldview differences.
So language is amazing for communication, but not perfect for knowledge representation for something like AI, where you need things unambiguous.
Yeah.
But the source mentioned how different ways of saying things in natural language can actually have the same underlying representation in a formal system.
Right, like logical forms in CNF. In logic, different surface expressions like it's not the case that A or B and not A and not B become the same standard form. Meaning can be consistent even if the surface language changes. And this is even connecting with how we're understanding the human brain.
That fMRI research with words, they showed people the word celery in an fMRI.
Yeah.
And they could predict what word they were thinking about based on brain activity.
Cutting edge stuff. They're even starting to predict brain patterns for words, even people, that the system hasn't seen before.
Yeah.
Suggesting there might be some shared neural code for meaning between us. It's early days, but really cool.
It is. The source pointed out that in logic, having different representations of the same knowledge doesn't change the facts you can figure out.
Sure.
But it can affect how efficiently you do it.
Yeah.
And for learning, representation is crucial.
Absolutely. Two logically equivalent statements might lead to the same conclusion, but one could be way faster to process. And for AI learning, how you structure info massively impacts what patterns it can easily pick up, what rules it can form. A good representation makes theories concise, easy to grasp.
Okay, so we've got natural language, good for us, but not perfect for AI. Propositional logic, better, but struggles with general rules about many things. That's where FOL comes in, right?
Right. FOL tries to take the best of both. It builds on propositional logic, the declarative, compositional, context-independent style, but it borrows from natural language to be much more expressive.
Like what? What does it borrow?
Think about a sentence. Nouns and noun phrases, they point to objects, the table, John's car.
Right.
Then verbs and verb phrases with adjectives, adverbs, they describe relations. Is on is larger than is blue.
Okay.
And functions, they're like special relations where every input has one output. The mother of, the capital of.
So FOL lets us represent these objects, relations, and functions.
You got it. We have constant symbols to name objects like Richard Lionheart, predicate symbols for relations like Brother Richard Lionheart, King John, and function symbols for functions left leg off, King John. Relations can be unary, just describing one thing like isking King John, or inary, connecting multiple things. When we say a predicate has an arity of two, like Brother XY, it just means it links two things.
Okay.
The source had some great examples of breaking down statements into these parts, like 1 + 2 = 3.
Yeah, that one stood out.
The objects are 1, 2, 3, even the result of 1 + 2. Equals is the relation, and plus is the function. Input 1 and 2, output 1 + 2.
Neat. What about squares neighboring the wumpus are smelly?
Okay, so there, the objects are wumpus and squares. Smelly is a property of a square, a unary relation, and neighboring is a binary relation between a square and the wumpus.
What about evil King John ruled England in 1200?
Even that works. Objects are John, England, 1200. Rule during is a ternary relation connecting those three.
Yeah.
And evil, king, are properties of John.
It's amazing how it all breaks down.
Right. And that's FOL's power. It's all about objects and their relations, making it super valuable for math, philosophy, AI, because so much of how we think, even in daily life, is about objects and how they connect. And FOL lets us talk about some or all objects, essential for general rules.
So FOL gains this power by dealing with objects and relations. The source also talked about ontological commitment. What's that all about?
Ontological commitment is like the assumptions a language makes about what exists in the world, what's real, basically.
Okay.
In logic, we see this in the models that tell us when a sentence is true. So propositional logic is committed to the existence of facts.
Just facts, huh?
Yeah. It assumes there are statements that are either true or false. A model in propositional logic just assigns true or false to each basic proposition.
And FOL has a bigger commitment.
It does. FOL says the world is made of objects and relations between them.
Okay.
So FOL models are more complex. They include a domain, the set of all objects that exist, and an interpretation, which maps our symbols to these objects and relations.
So it's like FOL is built for worlds where things are clear-cut, either true or false, but the real world is messy with lots of maybe situations.
Exactly. And that's the key point. Figure 8.1 in the source has a table summarizing these commitments for different logics. Worth checking out.
This ontological commitment sounds powerful though, right? Like you can figure out new truths from old ones, especially in areas like math or the Wumpus world.
For sure. In those areas, things are black and white. A Wumpus world square either has a pit or it doesn't. No in between.
Right.
This lets us do some serious deductive reasoning. But in the real world, things are rarely that simple.
Yeah, like trying to describe a city as large.
Right. Many real-world concepts are fuzzy.
Vague boundaries.
Yeah. FOL, in its standard form, struggles with that.
The source mentioned ways to handle that vagueness, like refining your representation or using fuzzy logic.
Right. Instead of just large city, you might have a function like population city and define large based on population. Or fuzzy logic lets statements be partially true, like 70% true.
Interesting.
Better captures our intuition about vague stuff. Often makes the logic more complex, though.
Trade-offs. And then there are even more specialized logics, right? Like temporal logic for dealing with time.
Right. That one builds time right into the system.
Yeah.
So you can say, it rained yesterday, or it'll be sunny tomorrow.
Okay.
And higher order logic is even wilder. It lets you treat relations and functions as objects themselves, so you can talk about them. It's even more expressive than FOL.
Wow. So ontological commitment is what the logic says exists. What about epistemological commitment?
Epistemology. It's about what an agent can know about those facts.
Okay.
What states of knowledge are possible.
Okay.
In propositional and first-order logic, it's pretty simple. For any sentence, you can believe it's true, believe it's false, or have no idea. 3 states.
Simple enough?
Probability theory, though, is more nuanced. You can have any degree of belief from 0 to 1, like 75% sure something is true. Fuzzy logic also has degrees, but they're about how true a statement is, not our certainty about it. Important distinction.
Yeah, that probabilistic Wumpus agent example helped. It could be like 20% sure the Wumpus was in one square, 80% in another.
Exactly.
All right, we've got the general idea of FOL with its focus on objects and relations. Let's get a bit more technical now. Syntax and semantics.
Time for the nitty-gritty.
The source said that FOL models connect our vocabulary to, well, actual possible worlds. They determine if sentences are true or not.
Right. Remember propositional logic, where a model just assigns true or false to each proposition. FOL models are way more detailed. They have a domain, which is all the objects in that specific world we're thinking about, and an interpretation, which is like a set of rules, connecting our symbols to those objects and their relationships.
The source used that example of Richard de Lionheart and King John with legs and a crown and all that. How does FOL handle that?
So in that model, the domain would be Richard John, their legs, the crown, all the things in that scenario.
Okay.
The interpretation says, like the symbol Richard Lionheart refers to the actual Richard object, King John to the John object, and so on.
Gotcha.
Predicate symbols, like brother, would link to the actual brotherhood relation. Unruh relations, like isking, would point to the set containing just King John.
Assuming Richard wasn't a king there.
Right. And the left legs function, given Richard, it gives you his left leg object, and so on. Figure 8.2 in the source shows this visually.
They mentioned total functions in this invisible object thing. To deal with functions that don't really make sense in some cases, like the left leg of a crown, that was a bit weird.
Yeah, it's a technicality of standard FOL. Every function must have an output for every input. So if something doesn't have a left leg, like a crown, we just say it has this invisible object as its left leg. As long as you don't say anything specific about the left leg of a crown, it doesn't really affect things.
Good to know. So what are the basic building blocks of FOL? What's the syntax?
3 main types of symbols. constant symbols, which are names for objects like Richard Lionheart, crown. Then predicate symbols, they represent relations, brother, on head.
Mm-hmm.
And function symbols for functions left leg off, father of. Usually they start with a capital letter by convention.
Okay.
Each predicate and function also has an arity. That's just how many things it connects or acts upon, like brother XY has arity 2, it links 2 things.
Right, right.
And the interpretation, that's what actually connects these symbols to real objects and relations in that specific world we're modeling.
So in our Richard and John example, the intended interpretation is like Richard Lionheart refers to the historical dude, brother to the sibling relation, and so on. But there could be other interpretations, right?
Lots of them. In another model, Richard Lionheart could be the ground, King John, a leg. It's our knowledge base, the sentences we state, that rules out the interpretations that don't fit reality.
Like our knowledge would say, no, Richard Lionheart isn't a crown, he's a person, and so on.
Exactly.
So a FOL model is a set of objects, the domain, plus the interpretation that links symbols to them. And like in propositional logic, entailment and validity depend on all possible models.
Yes. A sentence is valid if it's true in every possible model, and one sentence entails another if the second one is true in every model where the first one's true. But here's the catch with FOL. There can be infinitely many possible models, even if we limit the objects. So we can't just list them all in check like we sometimes could with propositional logic.
Infinitely many, wow. Yeah, checking those one by one isn't going to work. So how do we even make statements in FOL? The source started talking about terms.
A term just refers to an object. The simplest are constants, which are directly named things, and variables, which can stand for anything. But we can use functions to build more complex terms. Like, instead of a constant for John's left leg, we can say, left leg off King John.
So functions give us a way to describe an object instead of just naming it directly.
Right, and it's key to remember that complex term is still just a name. It's not like calling a function in code where it actually does something.
Okay.
We can talk about left legs without needing to define how to find them.
Right, right. And the meaning of a complex term, like ft1, tn, comes from whatever f refers to in our model, and the objects t1 to tn refer to.
It's all about what the interpretation says each symbol means.
Okay, so terms refer to objects. How about making actual statements with the source called atomic sentences?
An atomic sentence, or just an atom, is the most basic statement. It's a predicate, followed by terms in parentheses, like brother, Richard Lionheart, King John. It just says the brother relation holds between those two objects.
And these atomic sentences can use complex terms too, right? Like married father of Richard Lionheart, mother of King John.
Exactly. That one uses functions to pick out specific individuals, then says they're married. An atomic sentence is true if the relation actually holds between those objects, according to the model.
And then, like in propositional logic, we use those connectives and or not implies to build bigger sentences.
Yep, same syntax, same meaning as before. We can have things like brother left leg, Richard Lionheart, King John, or Isking, Richard Lionheart, Ising, King John.
Okay, cool. Getting more complex. Now we're at quantifiers, universal and existential. These are what let FOL talk about groups of objects without naming each one.
That's the key. Quantifiers are a big deal. What really sets FOL apart from propositional logic.
Let's start with universal, the for all symbol. The source said this is how we express rules like all kings are persons.
Right, in FOL that's XSX king. X is person X. For all X, if X is a king, then X is a person. SSP is true only if P is true for literally every object, no exceptions. And there's a common mistake here, using and D instead of implies.
Okay.
If you wrote X is person X, it'd mean everything is both a king and a person.
Which isn't what we meant at all.
Nope. The implies ensures the rule only applies to things that are kings. If it's not a king, the whole thing's automatically true no matter what.
The implicit focuses on kings then. Got it.
Yeah, exactly.
Now, existential quantification, the there exists symbol. This says at least one thing has a certain property. The example was King John has a crown on his head.
Right. In XSEO, that's X is Christian's on head.
Okay.
There exists an X such that X is a crown and X is on John's head.
Okay.
Here, ND is the right connective. Using implies usually makes a weak statement.
The source said that.
Yeah, like just crowned X is King John would be true even if there were no crowns, because the implies is only false. There's a crown that's not on John's head. If there are no crowns at all, the whole thing's true, which isn't what we meant.
Subtle but important.
Yeah.
So, for universal stuff with era for existence claims, what about when we combine quantifiers? nesting them.
Nested quantifiers get us into really interesting territory. If the quantifiers are the same type, you can sometimes shorten it. Like Yuri's brother XY becomes Yuri's, where E's a brother XY.
Yeah.
But with different types, order is crucial.
Like, everybody loves somebody versus there is somebody who is loved by everybody.
Exactly. Scary. It means everyone has someone they love. But Erix loves
Hmm.
XY means there's one specific person loved by everyone. Big difference.
Huge difference.
Yeah.
And the source said a variable scope, what it refers to depends on the innermost quantifier that introduces it.
Right. Best to use different variable names to keep things clear.
Good practice. Lastly, on quantifiers, the source mentioned how they connect through negation, like De Morgan's laws.
Oh yeah, they're closely related. Like everyone dislikes parsnips is the same as there's no one who likes them. Echo X parsnips is equivalent to Jess likes parsnips. Same idea with the somebody likes broccoli example.
Mm-hmm.
We can technically use just one quantifier, but having both makes things more readable.
Okay, last bit of FOL syntax, I think. Equality with the symbol.
Right. Equality is special. It's a built-in predicate that says two terms refer to the exact same object, like father of John. Henry means John's father is Henry. Not just someone similar, the very same individual.
And we can use negation with equality to say things are different, right?
Yeah, which is how we say things like, Richard has at least two brothers. We write XE is brothers X, Richard is brother X,
Mhm.
X, Y.
Okay.
So there's an X who's a brother, he's a brother, and they're not the same person. At least two distinct brothers.
Gotcha. Now, this syntax and semantics section ended with database semantics as an alternative to the standard FOL. What's the main difference?
Database semantics is like a simplified version, common in databases and logic programming. It has three main assumptions. Unique names, every constant name's a different object. Closed world, if a fact isn't stated, it's false. And domain closure, only named objects exist.
So it's like a more contained view of the world.
Exactly. Under those rules, Richard's brothers are John and Jeffrey. It's just his brother, John Richard, his brother, Jeffrey Richard. We know they're different people because of the unique names assumption, and we know there are no other brothers because of the closed world assumption.
Makes sense. Why not always use database semantics then? Seems simpler.
Because those assumptions aren't always true or even what we want.
Okay.
The closed world one is risky if your knowledge is incomplete. You might assume something's false just because you haven't heard about it. Standard FOL is more flexible, allows for unknowns. It can be more complex sometimes, but it depends on the domain, what kind of knowledge we're dealing with.
For the rest of this chapter, though, they stick with standard FOL, right?
Yep. Pointing out when it gets a bit messy, though.
Okay, good to know. So we've got the language at FOL now. Terms, predicates, functions, quantifiers, equality. The next part is how we actually use it.
Knowledge base is right.
Right. Just like with propositional logic, we build a knowledge base, or KB, by adding sentences we believe are true. Usually we call this tell.
Like we tell it, John is a king in FOL, or all kings are persons.
Exactly. And then we can ask questions using ASK. If our query follows logically from what's in the KB, it returns true, otherwise false.
So if we told it John's a king, all kings are persons, then ask A if John's a person, we should get true.
We can also ask more general things like, does there exist a person? But sometimes just yes or no isn't enough. We want to know who that person is or what specific values make things true.
That's where askvars comes in. It finds those values.
Okay.
Like askvars KB, as person XEs, would hopefully return John, Richard, whoever we know is a person. The force mentioned that askvars works best with horn clauses, a specific kind of FOL sentence.
Right.
In more general FOL, a query might be true without there being specific values that make it true.
Interesting. So we tell to add knowledge, ask var to check what follows logically, and ask vars to find specific instances. Now the source gets into how we can use FOL in different areas. Kinship relations is the first one.
Family relations are a classic example for FOL. Our objects are people.
Right.
We have predicates like male, female, parent, sibling, spouse, and functions like mother, father.
And FOL shines when we write axioms to define these, right? Like, mother is a female parent.
Exactly. That'd be something like MAAC, female M, parent MC. For any M and C, M is the mother of C is and only if M is female and a parent of C.
Nice.
We could define husband, grandparent, sibling, all like that. The source even has an exercise for this, 8 keygens, if you want to try it yourself.
I might just do that.
Yeah.
So these axioms are the basic rules of our kinship world. And then some things, Like siblinghood is symmetric. They're not axioms, but theorems we can figure out from the axioms.
Right. XY sibling, XYX. If A is a sibling of B, then B is a sibling of A. That follows from how we define sibling using parent.
Makes sense.
Technically, a KB only needs axioms, but using theorems makes reasoning way more efficient.
Otherwise, I'd have to rederive every little thing from scratch all the time.
Exactly. The source pointed out, though, not everything in our KB has to be a definition. Some things are just facts, like male Jim or spouse Jim, Laura. And sometimes we realize our axioms aren't enough to get the conclusions we expect.
Meaning we're probably missing something crucial.
Yeah, like knowing Jim's married to Laura, we might assume George isn't married to Laura. But our axioms might not allow us to actually conclude that. We might need to add an axiom saying person can only have one spouse at a time.
Okay, good point. Then the deep dive moved on to numbers, sets, lists, all those more abstract things. Defining natural numbers with the Peano axioms was super elegant, like building up all of arithmetic from just a few basic rules.
Yeah, the natural numbers 0, 1, 2, and so on. It's a great example of FOL's power. We start with the predicate net.